Okay, so I've set up a little scenario here where we have a light bulb on a loop of wire, and that loop of wire is in a magnetic field, and we are pulling it out. We're pulling it out at a velocity of 3 meters per second. I gave you the distance between one side of the loop and the other, and the question is, what is the potential difference in the light bulb at this point? So let's go through and talk about this. If we want to do it, I'm going to show you the long way, and I'm going to show you the short memorization way. All right, the long way is this. Of course, if we want the potential difference, we're going to have to find our EMF here, which is the potential difference. It's change in flux over time. Believe it or not, I do not memorize basically anything in magnetism. I just go back to this equation every single time. I have a couple other ones memorized, but this guy is kind of the heart of the whole thing. It is important to know what makes up flux, I should say that. That's magnetic field times the area times the cosine of the angle. And if you don't understand this cosine of the angle, check out one of the other videos where I talk about what the area vector does, okay? In this situation, right now, our flux is the magnetic field isn't changing. The angle isn't changing because we're not rotating the loop. So what's going to be changing is this area. What makes up this area? Area is the length times the width. We'll just call this from here to here the width. We don't really need to think too much about it because it's going to be gone in a second. Let me show you why. Okay, so we're going to go over here and change in flux. Okay, so our flux final minus our flux initial. That's one way to think about it. Our initial, our original flux had this magnetic field. It had a certain length. The length isn't going to change. The length is this 2 meters. That doesn't change at all. However, the width is going to change. So width final. And that's not the width of the whole thing. Ooh, I drew that terribly. Please ignore me. It's not the width of the whole thing. It is the width that is inside of the magnetic field, because that's the only part that contributes to the flux. Okay, see, I did that intentionally so you could see adults making mistakes. It's really important in education. Really, really important. So B, L, and now our width initially. So initially, a certain amount of this was in here. We're going to pull, and there's going to be less width. But again, that's going to matter in a second, because I'm going to show you how we can make this into a much shorter equation. So B, L, and final width minus initial width over time. In other words, BL, the change in the width over time. Well, how fast you are changing that width, okay, ends up being how fast you are pulling this guy out, okay? It's your distance divided by time. So what does that mean? This whole fancy, disturbing equation basically comes down to BLV, where V is the speed you're pulling it out at. So in other words, you can actually just memorize this for these kind of problems. So that's the short answer. Let's use that to do the actual problem. At this point, the problem basically becomes a plug and chug. So that's going to be our potential difference. The magnetic field was 0.3. The length is that 2 meters. And the velocity is 3 meters per second. So math is 1.8 volts. Okay, so that is the potential difference. So now what would be the, okay, what is the current in the light bulb? Okay. Great question. Of course, we would go to Ohm's law, okay, which you can also write, boop. So 1.8 equals the current, and the resistance is 2. So the current is 0.9 amps. Yay, I feel smart. So how much work would it take to pull this thing out? Or to keep it going at 3 meters per second? Well, let's take that apart. If you remember, work from last year is equal to the force times the distance. We have the force, and they gave us, did they give us the total length? What did I originally give you? Okay, they didn't give us the total length, so I'm just going to make one up here. Okay, if that was 2, let's say this is 3.5 meters. Okay, so to pull the whole thing out, you would have to move it, hold on. You would have to move it 3.5. So that's the distance you would have to pull it. The force that would be fighting you the whole way is that 0.54. So to find the work, it's work is equal to force times distance. So force is 0.54, and your distance would be 3.5 meters. And we get from math 1.89 joules. Okay? You're like, where is that energy going? If I'm fighting and I'm losing 1.89 joules, what is that doing? Well, that's making our little light up. Because none of this is free energy. This all comes down to the conservation of energy. You are doing work, and that work is turning into electricity. You are gaining no energy. In fact, if we're going to be really technical about it, second law of thermodynamics, some is going to have to be lost as thermal energy. This is a very ideal situation we just did. Please keep in mind that you're not making energy. You're just making electricity. You're giving energy to do that.